So similarly, there are other features which take into account both texture and shape, and those are wavelet features. So a lot of these you can find in other courses, but just be aware of what are some useful features that can be extracted from different specialized types of data, such as images. Now, keeping with the same theme, let's talk about audio features. So what is audio? Audio is basically, you have a time axis and then you have a pressure waveform. Right? So this pressure waveform usually is sampled at 20 kilohertz or 40 kilohertz. Right? Why? Because that is the limit of frequencies that a human ear can reliably hear. After that, it becomes ultrasound, and which is something that we don't hear, but other animals can, such as bats that use it for navigation, or we use it for specialized applications such as medical imaging. Now, so if we sample this audio signal, basically we get a lot of samples. And the other problem with this is that we don't know about different audio samples how long they will be. So for example, let's say if we are doing automatic speech recognition or automatic emotion recognition in speech, then whether someone will take long time to speak a particular sentence or a short time, we don't know. It depends on the person, and it also depends on when they speak. If they repeat the same sentence, it could be of a different time. So we want to extract features that are meaningful for audio, and yet they are useful for the task at hand. And what has been observed by a lot of research into sound is that the frequency component, the power in different frequency bands of an audio signal is important. So what that means is that we take the raw signal and we take its Fourier transform. Okay, and then Fourier transform will basically tell us what is the low level frequency, what is the mid level frequency, and what is the high level frequency, what is the relative contribution of each of these frequencies in this particular wave. So if I take different sinusoids with different weighing factors and I combine them, I should be able to get this original waveform back. Alright, and then these sine waves can also shift left and right, which is the change in phase. And many times in applications, when we are extracting features, we ignore the phase. But that's another whole topic that I don't want to get into, because phase itself can be important, and there are better ways of extracting features where phase is also given due consideration. But most of the time we are happy with looking at just the absolute value of the contribution of each frequency, so which is the power spectrum density. And now what we can see is that different windows in this particular time signal can have different frequency components. So for example, if someone is singing and they are singing a different portion of the song, they might be hitting some high notes, whereas in another portion of the song they may be actually working with low notes. So a Fourier transform by itself is not that useful. We do some kind of a windowing, so we look at different time windows and we do the Fourier transform of each of these windows separately. So so what I'm getting at is there is something called Mel frequency cepstrum coefficients, MFCC, Mel frequency cepstrum coefficients, which is one of the default features that are extracted from audio waveforms. And the algorithm, in a very quick way, without getting into a speech processing type of a course, is the following. Basically, we will first do windowing, which means for the pressure waveform we will look at different overlapping windows in time. Okay, so this window is only looking at this portion of the signal, the next window is looking at the next portion of the signal, and so we'll look at several overlapping windows of the same signal. And for each window, what we will do is we will compute the discrete Fourier transform. Okay, and once we have the discrete Fourier transform, from that we will get the power spectrum density, which means what is the power contribution by each of those frequency bands. Then we will basically do something called a filter bank. with log energy bank, BANK, and log energy. We will find the log energy. So what that means is that once we are looking at different frequencies now, not time but frequency, right? So the frequencies can range from 0 to, let's say, 20 kilohertz. We will have these different overlapping bands, but the size of the bands will keep expanding as we go, right? Because when you are in higher frequencies, the change in frequency has to be large for it to matter. When you are in lower frequency, the change in frequency has to be small to matter. So when we pool different frequencies together, we have some central frequency, and we also take contribution from neighboring frequencies, but that neighborhood is large when your central frequency is large. So we use such a filter bank, and based on that we get the contribution of different frequency bands, and then we compute something called discrete cosine transform, and that's how we will get the MFCC coefficient. Another useful feature of that can be extracted from audio is something called spectrogram. So we have time on one axis, and we have frequency on the other axis, and we basically have a two-dimensional array, right? So basically in a particular time window, so if I look at a particular time window, what are different frequency band, the energy contributions of different frequency bands, that's what it captures, and that can be used as a feature provided that the number of time windows is fixed for different samples, and the number of frequency bands is also fixed for different audio samples. So these are some ways to extract features from audio, and some features to extract from text are the following. So let's say we are now looking at natural language text. So let's take an example of a text. The cat was chasing the rat. Okay, so let's say this is a sentence, and I want to extract different things from it. So I want to, let's say, classify this into positive or a negative emotion. So maybe let's take something less neutral than this. I got lucky in the test today, right? So this is LUCKY, lucky in the test today. So this is definitely a positive emotion, and let's say we want to extract, we want to classify this into a positive or a negative emotion. And let's take another example. I was not very lucky today. Okay, so this is another person using the same word lucky, but that this person is expressing a negative emotion. So some common text features that we can extract are, the first one is just a histogram of words. So what I mean by that is, let's say we have a dictionary, and in the dictionary we have we can start with a and the, but a and the usually don't matter because they are in every sentence and they don't really help you figure out the emotion of the sentence. But let's say I have starting from a and then some other word and whatever, and then I have I, and then I have somewhere I have got EFGHI, no, got will be before I, so got, and then I have I, etc, etc. So I have a dictionary, and for each sentence I will put a number in the dictionary, that here I had one, here I had one, and then for in I had one, and etc. So now I have a feature vector which is mostly zeros, and some places it has ones that encode the words that appeared in that particular sentence. And if we are classifying paragraphs, then we may have more than one, this one may become two, and so forth. And if we want to normalize it by the size of the sentence or the size of the document, we will divide it by all the number of words, and then it will be some fractional value such that the entire vector, all the components add up to 1, but each component itself is between 0 and 1. So that would be one way to encode features, which is basically just the frequency of the vocabulary that you have. So that is usually a good feature to start with, and then we can train classifiers on that. Now those classifiers, if we have a binary classifier for positive emotion versus negative emotion for sentiment analysis, that might be able to figure out that if these two appear together, then it's a negative emotion. If this appears by itself, then it is a positive emotion. We may or may not be able to get it. Now, one problem with this is that we are putting an emphasis on all the words together, right? We are not using, making an adjustment for common words that are less informative because they appear everywhere, right? So for that, there is a slight variation of this term frequency histogram, and that is called TF-IDF. So TF is what I just described, which is term frequency. And this is inverse document frequency. That means basically it encodes whether this term differentially appears in this particular document as opposed to other documents. By document I mean the sample, which could be a paragraph or a sentence or a complete document. But whatever is the sample, document means sample. So does this term appear differentially in this document and or in a few documents, and because of that its appearance is important. If it appears in too many of them, then it is not important. So let's look at this carefully. What is your TF? TF is based on the term and the document. Okay, TF is a function of term and the document. It is the frequency with which the term appears in the document, okay, divided by sum over all the terms tau that belong to this document. Okay, basically it's a normalized count of the term in this particular document. But now we want to temper this for those terms that appear in lots of documents, and that's why they are not important. Okay, the terms that rarely appear, they are more important. So for that we will also define IDF. Okay, here we will look at not just the term T, but we'll look at entire set of documents, capital D, not small d, capital D. Capital D is a collection of small d's, so we call this corpus of documents. Okay, and here we will have log, okay, of the total number of documents in the corpus divided by 1 plus, okay, the documents in which these terms this term appears, D belonging to D, such that T belongs to D. Okay, so the total number of documents divided by the number of documents in which only this term appears, or this term appears, right? So here the numerator, when it is small, you will get a large value. If the numerator is large, then you will get a small value, right? So that will temper the IDF. So basically your entire feature for one term will be TF times IDF. Okay, so this is one popular feature that is used for text. Another way to use features, to get features, is to use pre-trained deep neural networks. In this course, we will unfortunately not be able to cover a lot of deep neural networks, but the concepts of machine learning is still important with pre-trained deep neural networks and with deep neural networks themselves. So what you can do is, let's say you have an image, right? You can send it to a very deep neural network. I will call it CNN. Okay, so it takes the input in form of that two-dimensional matrix of pixels, but the output that it gives is a one-dimensional vector, and let's say the dimension of this vector is 512 cross 1. Now the weights of this neural network, or the coefficients of the neural network, are fixed. because it is pre-trained on a very large set of images, and it is trained in such a way that these 512 numbers that we have extracted from a very large image are meaningful. They are somehow representing things that are of importance in the image. We assume that we are not going to change the neural network, but now we can take these 512 features for different images, and you can use them in different classifiers, like a logistic regression classifier, in a support vector machine, in a perceptron, or in a decision tree, and we can classify images based on just these extracted features. We can do the same thing with text, where we can take a large pre-trained neural network for text, such as GPT-3, and use that, the features that are extracted from that, summarize those features for the entire sentence, and use that for something like sentiment classification and so forth. So the theme that we are looking at is that there are various different domain specific ways of extracting features that are based on prior knowledge about interaction between variables, or how the variables are entangled together and so forth. So when we introduce these new features, we usually have a lot of features together, right? So we have sometimes more features than we can deal with it, because a lot of these features could be confounders, or they could be correlated and so forth. So reducing the number of features becomes important, and that is the topic of the rest of the lecture.